Hi, welcome back to our lecture on a practical guide to quantitative finance interview. Today, we will continue our last topic, calculus, and we are going to introduce a few important calculus methods like Taylor series, polar integration, and also things like LaGrange multipliers. Okay, let's start. So first is about polar integral. So what is polar integral? The polar integral is trying to change a Cartesian integral into a polar integral, which means the variables in two-dimensional plane can be mapped into polar coordinates with x equal to a radius multiplied by a cosine theta, y is equal to the radius multiplied by a sine theta. So we are changing these two variables, x and y, to r and theta. And the explanation could be illustrated by this picture on the right-hand side. So basically, we have a circle with the radius r, and we are converting the x and y, the two lengths of this triangle, to convert it into the formula of r and theta. And now it's trying to use this method to solve this problem here. So the problem is trying to ask if x is the standard normal random variable, which means it follows the standard normal distribution, 0, 1. What is the expected value of x, conditional on x is larger than 0? Well, so let's first write the distribution here. The PDF of n01 equals to fx equals to what? 1 over square root 2 pi multiplied by e to the power negative x to the square divided by 2, right? And how can we solve this problem if we do not know the polar integrals? Well, it's actually a classic example of using integration by substitutions, which we introduced during the last lecture. So we can let u equals to negative 1 over 2 x squared. And what is going to happen? So we can replace this part as EU, right? So it is gonna to be the same as if we take the expectation of x larger than 0 is going to be 0 to negative infinity. Please take notes here. Actually, this negative infinity is on the top. And why it is the case? Because originally we are going to take integration of this one, right? X multiplied by this part dx, right? And now, what are we going to do? We are going to convert u to x squared. So because x is from 0 to positive infinity, so u is going to from what? It's going to from negative infinity to 0, right? So when x is 0, u is also 0, right? So this has to be 1-on-1 map, and this will be negative infinity. Because when x is 0, u is also 0, but when x goes to positive infinity, u is going to be negative infinity. Okay, so this is going to be 2 pi e to the power u du. Okay, why it is the case? Because if we take the derivative of du equals to what? Equals to dx equals to negative x, right? So by solving that, we are going to have this equals to 1 over 2 square root pi. So it's also easy, but I mean, if we change it with the polar integration, then we can think it as a unit circle. How it is that? So for this part, it's actually 1/2 of this one, right? It's just 1/2 negative infinity to positive infinity e x squared dx, right? And how can we solve this one? We know that if we have a circle of, if we have a formula like this, again, so we can use integration by substitution to solve this problem, but I'm just trying to show you another way to solve it geometrically by Pauling equation. So we have these two similar equations converted from here. So we just define a new y, and then we can change them into this one, 0 to 2 pi. Because it's all around circle, you know, a classic circle is x squared plus y squared equals to 1, right? So we have a circle and x, y, radius, r squared. Let's write it here. And this theta, the range of theta is from 0 to 2 pi, while the range of radius, as long as it's positive, is okay. So it's going to be the same with, and remember the fraction divided by 2, dx also. So we have been changed that by using the formula here. So it is going to be negative r squared cosine square theta plus sine theta squared divided by 2 and multiplied by 1r, remember that, dr d theta. And because if you have learned about if you apply some middle school math knowledge, we can know that this is equal to 1. So it's actually, this part is going to be e negative r squared over 2, right? And then this is gonna, we can first move this one in because all this part is not related with theta. So we first integrated out 0 to pi d theta, right? And for the first part, it's what? It is actually e negative 2r over 2 and d negative r squared over 2, right? Just similar as our solution in the integration by substitution method. So this is going to be theta 2 pi 0, and this is going to be negative, while this range is what? 0 to infinity, right? By taking that, we can have this one is equal to pi square root pi over 2, and we only want a half of that, so just divide it by 2, so we can have 8 pi, right? We have solved that. Okay, now let's come to Taylor series. I personally think it's the most elegant and the most important method for all important tricks in calculus. The one-dimensional Taylor series expands function fx as the sum of the series using the derivative at the point x equal to x0. Because we are actually taking the distance of that, so and we can trivially choosing any x0. So usually we choose x0 at 0. Okay, so just for convenience. But sometimes we may also use 1 in some special questions. And please remember this format. I hope you all be very familiar with that, and I believe it is going to be widely applied as you will see in the next few questions. So if x0 equals to 0, then we can see fx is going to be equals to f0 plus f's first derivative multiplied by x. This is actually 1's factorial plus 2's factorial. And now the numerical, it will be the second order derivative and multiplied by x squared and all the way to go. And there are three most important things I hope you to remember. The first one is EX, okay? So EX is also gonna to be like this one. Without the sum limits and equal to 0 to infinity, okay? And it can also be represented as 1 plus x squared over 2 factorial plus x to the power of 3 factorial. Okay. And also for the sine cosine, you can see it's just the same as this part. We just take the array set all the even part of EX while changing each even one, like 2, 4, 6 as -1, while others being positive. And the things left is the cosine. Okay. And these two actually is gonna to got the Euler formula, the famous Euler's rule. Okay, we are going to talk about that later. So okay, it's here. So it is asking what is I to the power of I. So to solve this question, we need to first know this one. This is basically like the Euler's rule. Okay. So for this Euler's rule, okay, so it's just, so this one should be spelled as Euler. Okay. So for this Euler's rule, how could we prove that? Well, it's actually quite easy because we already have this one, right? EX. So EI theta is going to be what? It's going to be 1 plus 1 factorial I theta plus 2 factorial I theta square plus all the way back, right? And we know that I square is going to be -1. So it is going to be 1 plus I theta minus 2 factorial. And on the top it will be theta square plus 3 factorial and theta to the power of 3 I and what? -1 and plus 4 theta 4, right? And all the way later. And because we already know the formula of sine and cosine, right? So we can see that this part is actually equal to what? Sine theta plus cosine theta. This will be multiplied by 1i because we have 1i here for each even items. Okay. So we prove this formula. EI theta equals to cosine theta plus I sine theta. I want to spend more time on this Euler's formula because I personally think it's the most beautiful formula or most beautiful rule in the whole mathematical world. You can see it if we take theta is related with pi, right? So you see it puts theta e, the natural number, I, the complex number, the complex index, theta, the pi, right? Together, in one formula. And if we take theta I2 pi, this cosine 2 pi is going to be what? It is going to be 0, right? And sine 2 pi, it is going to be oh no, sorry. Cosine 2 pi is going to be 1. And sine 2 pi is going to be 0, right? So all the basic elements in math are put here together into one formula in a super elegant and simple way. And it's balanced, okay? That's why this Euler's formula is so classic. Okay, so let's see how can we solve this question once we know the Euler's formula. So we now know that EI pi is gonna to be what? It's gonna to be cosine pi plus I sine pi. And sine pi is also going to be 0, so this part is canceled out. So it is going to be cosine pi, which is -1, right? And if, let's say theta is equal to pi over 2, then EI multiplied by pi over 2 is going to be what? Cosine pi over 2, which is equal to 0, plus I sine pi over 2, this is equal to 1, equals to I. So log in I is going to be what? It's going to be log in EI multiplied by 2 over pi. It is gonna to be I multiplied by pi over 2, right? So log in I to the power of I is going to be I log in I. It's going to be I to the square multiplied by pi over 2, which is negative pi over 2. Okay, so I to the power of I is going to be E to the power of negative pi over 2. We solved that. And for the second one, I believe it's super easy for you to get that. So basically, we just need to define the function and trying to solve it using Taylor's formula. So what kind of function are you trying to use? Well, let's first just define fx as what? As 1 plus xn, right? So fx first order derivative is going to be what? N multiplied by 1 plus x and n minus 1, right? And how about second order? It is going to be n minus 1, 1 plus x to the power of n minus 2, right? Then applying the Taylor's formula, fx is going to be fx0 plus fx0's first order derivative, x minus x0 plus 2 second order derivatives, x minus x0 squared, and all the way. So we take x0 as 0, right? So it is going to be 1 plus, if we take 1 here, if we take 0 here, then it will be n multiplied by x plus by all the residual. Let's put it as residual x, okay? So this part, because residual x must be greater than 0, and then this fx is gonna to be larger or greater than 1 plus nx. So it's quite simple to be solved. So maybe you may ask why this residual part must be larger than 0. Well, it's actually quite easy to get that. So let's first look at the second order. Second order is something like n multiplied by n minus 1 and multiplied by 1 plus x n minus 2, right? X squared. This part is gonna to be larger than 0, right? Because it has something like n minus 2, and this part is going to be larger than 0, right? And we know that x is larger than -1. That's a reason. And for all the things later, for the fourth, fifth item during the Taylor expansion, it will be also the same case. And basically, we can prove that this residual part is greater than 0. And now let's come to the Newton's method. So Newton's method, okay, is also known as the Newton-Raphson method. Okay, that was Fourier. So it's basically an iterative process for solving the equation fx equal to 0. It's trying to finding the root solution by taking the slope each time. So we have a function, and this is going to be like xn, and this is fxn, right? And the derivative here is going to be f slash xn, basically the slope. And it is trying to put this value divided by this value, okay? So, and to take the gap, move it a little bit forward to get x and plus 1. And one of the things that I hope you should notice that the convergence of Newton's method is actually quadratic, which means it's fast, and it's faster than other two methods I'm going to introduce later. But the problem is that the convergence is not guaranteed, especially when the starting point is far away from the correct solution. So sometimes you need to pick a few points to see if it is going to converge, okay? And the iteration equation, actually, why it looks in this formula, is coming from the first order Taylor series. How is that the case? It's already written here, because we can have fx minus n plus 1. So if we define this, then we know that x0 can be taken as any value, right? So we just define x0 as xn. Then this is going to be what? Fxn plus the first order derivative of fxn. And this is xn plus 1 minus xn, and plus the second, third part, blah, blah, blah. So it is now using like it is almost equals to fxn plus fxn slash xn plus 1 minus xn, right? And we are trying to make this to be 0. Then what is going to happen? Basically, we can find now xn plus 1 is going to be xn minus fx divided by f slash xn. Okay. So we have some, so basically you know the reason. So maybe you may ask why we should let this fxn plus 1 equals to 0. Because this is what we are trying to solve it, or trying to solve that. We are trying to find the root, okay? We are trying to find the root of this kind of equation. And there are also two other root finding methods. The first one, I think, is the most intuitive one, is the bisection method. So basically, let's define x0 as the true root, okay? So we may start from something on the left, let's say a, and we pick another number, like we just starting from a range, like from A to B. So we first test FA and FB, right? And then we are going to try fa plus b divided by 2, the middle point. Okay. So as long as this one is smaller than 0 and this one is larger than 0, and then we test if this one is also smaller than 0, then we pick the next midpoint between a plus p divided by 2 and b. But if these two numbers, the sign of these two parts are different, then we find the middle point of this part until it converges to the true root. But this one, the convergence rate is linear. Okay, so it's slower than quadratic Newton's method. And it's same for the secant method. So the secant method is just trying to use xn plus 1 equals to xn minus 1, xn minus xn minus 1, fxn minus fxn minus 1 multiplied by fxn. So what is this? This is basically the thing, the first order derivative before we take the limit, right? Before we take limit delta x converges to 0. Okay, so although these three methods looks a little bit different, but they have the same logic. I think the secant and Newton's method are coming from the derivative. And bisection is just a very intuitive way to choose between the middle point and to getting closer and closer. Although it's linear, but it is going to be guaranteed its convergence. Okay. And last but not least, let's talk about LaGrange multipliers. This method of LaGrange multiplier is a common technique used to find local maximums and minimums of a multivariate function with one or more constraints. So what does it mean? So it means that if we have a function, okay, so if we have a function f x, y, x2 all the way to xn, it could be a function of xn variables, okay, and it could be differentiable, okay. And now we are going to maximize or minimize this function subject to a few constraints. It's actually quite common in linear programming. It's a super large topic called operational research, right? So the strengths, okay, constraints. So this one is the target function. Constraints we can also have like g1, x1, x2 all the way to xn equal to 0, and g2 the same equal to 0, blah blah blah, right? And the Lagrange multiplier is that we take fx plus what, lambda 1 multiplied by the ingredient of g1x. For this ingredient is actually a partial derivative of x1, x2 for each variables, okay? So now let's give it, and this is all the way to lambda n multiplied by the gradient of g and x constraint, and we take it to be 0. And let's see a real question. What is the distance from the origin to the plane 2x plus 3y plus 4z equals to 12? So the distance is the minimal value of s square plus y square plus z square, right? Because we are starting from the origin. So x, y, z, this is the origin, right? So if we are going to some kind of plane, this one must be orthogonal This one must be your signal. Okay, so we are trying to minimize. Okay, this is our target. Okay, target is to minimize x squared plus y squared plus z squared subject to g 2x plus 3y plus 4z minus 12 equal to 0. Then we can have what? Then we first take the derivative of this fx and gx according to x. Then we have 2x and this plus 2 multiplied by lambda x. Oh, there is only one. So there is only one subject, so there is only one lambda. And this is going to be 0. Meanwhile, 2y plus 3 lambda is also going to be 0. And 2z plus 4 lambda is also going to be 0. And we also have 2x plus 3y plus 4z equal to 12. And we combine these four together. We're going to have lambda equals to negative 24 over 29. X equals to 24, 29. Y equals to 36, 29. And z equal to 48 over 29. Okay? And then the distance, you just need to take all these squares, okay? And then take the square root, which is going to be 12 over square root 29. And actually in general, okay, so in general, a plane in 3D R3, okay, it has the format ax plus by plus cz equals to d, right? And the distance origin, okay, from the origin is going to be what? Absolute value of d over the square root of a squared plus b squared plus c squared. Okay, now I just finished introduced all three important techniques for solving calculus questions. And next time we are going to talk about ordinary differential equations. Hope you enjoyed this lecture and see you next time.